computer. This camera would be better for you, probably. There you go. Okay, so I probably should have fixed the title on this thing because we're not doing inequalities. They cut the inequalities out. But 5.6, we're continuing doing stuff with exponential and logarithmic equations. So we're going to do, this one's a lot of sort of word problems happening. So the first thing I guess that's on here is the exponential equation. So what is an exponential equation? It's an equation with an exponential. It's probably pretty much what that says. I don't know. Let me read it. An equation in which the variable occurs in the exponent of an expression. So that's pretty much it. It's an exponential function. Now you have it equal to some sort of number. And so hopefully if we realize if we have an equation, we're probably going to do some solving. Ooh, is that right? There's a dog outside, in case y'all didn't know that. The population P of Arizona has been increasing at an annual rate of 2.3%. In 2010, the population of Arizona was 6.4 million. And so the first thing we want to do is write a formula, P of X to represent X years after 2010. And P is in millions. And so we know this is exponential. I guess kind of the odd thing here is probably rewrite that as a decimal. We want to think about how much this is increasing per year, like what is the base amount of this? And this kind of relates back to when we were talking about like interest. If there was like a 3% interest, we would take like we wouldn't do, it would be an increase of like 2.3%, but if we want the total amount of the previous amount, we would have to add like 100% to that. And so like if you think about when we did the interest, this is coming back to like we have to have one of the original thing that we started with, and then we're going to take 23% more of that. And so a little bit more, if we go to this P of X, let me try to remember what variables they had. Was it CA to the X, I believe, was how they define things?
Yeah.
Yeah. And so if we want to know our A, our increase, the increase is going to be this thing, the 1 plus the 0.023. And so each time it's going to increase by 102.3% is basically what this thing is saying. So this is the A. This is the amount of increase. The C was like the initial starting amount, and I think it gives us that in the problem. In 2010, the amount that it started with was 6.4 million. And so this should be the basic formula that we're coming up with. The A, or the increase, it's increasing by 2.3%. An increase of 2.3% is 123% of. So this is like my other class, really they go over into like details of that vocabulary. It's more than, and this is of. Okay. And then the other thing is we start with 6.4, maybe like make a mental note, we're talking about like millions if we get a population. Estimate the population of Arizona in 2014. So if we're starting in 2010, 2014 is like what? What is that giving us to plug in?
4 years later?
Yeah, 4 years. So something is 4. What is 4? The X variable would be 4. And so I think like aside from like the words written into this problem, I think like the most of the math in this problem is kind of straightforward application of exponential, like we've kind of been doing. We're just plugging in, trying to find what it was 4 years later, 6.4, 1.023, 102.3%, and then we plug in the 4. And so definitely going to use a calculator to try to figure this thing out. I did it in my notes. 1.023 to the 4. Let's double check it. So I'm getting like 7.009, somewhere in there. And so you might as well probably going to round that to the nearest. It's about 7, and I think I said, what were we in? Millions? Millions. Okay. So they give you some steps for solving exponential equations. So this thing, they gave us a year and they asked us to find population. So they gave us an X, asked us to find a Y. The other way they could do it is give us the Y and ask us to solve for the X, which then we'd have to do some back solving with an exponential, which means we'd have to do a log. So we can do this like kind of both ways. This is I would say this is the more straightforward way. The other way is going to include some back solving of some sort. And so they give us some steps for solving exponentials, for solving logarithms, but I don't want to sound too much like a high school bully, but like it's kind of the same approach for everything else we've been solving. You're going to get the thing that looks weird all by itself. You're going to pick on the thing that looks weird, and then you're going to undo it, basically, right? You get the thing that looks weird, and you get it all by itself. I isolate the exponential expression on one side. We're getting it by itself. Once you have an exponential by itself, you take the inverse, which is the log. That gets rid of your exponential. And then, what does it say? Apply either inverse property or the power rule. Okay. So pretty much everything after that is just solving for a variable like we're kind of used to, hopefully. So the intensity I of a beam of light passing through water decreases according to that crazy formula. So that's an exponential with the natural log base. So we've talked about this E, it's Euler's number. It is, if I do it again, 2.7 something crazy. I couldn't tell you off the top of my head. It is that number, it's an irrational number. And so X is the depth in feet. Determine the depth X at which the intensity is 1%. And it says I naught. So the initial light that we're starting at is 500 lumens. Well, that's already kind of in this equation. So hopefully you notice that's where that number is coming from. We're doing it 1. And so if we want it 1%, okay, that's kind of a weird. Okay, it's kind of a weird question because we want 1%, and so if the intensity is 1% of 500, then you might figure it out. But we want to know when the intensity is 1% of 500. That is 5 lumens is what they're asking, right? And so you might have to do this little middle step before you even start plugging things in. They want to know when is this going to be 5 lumens. And so now we're just plugging this in. We're plugging this in place to our I variable. So 5 is equal to what? 500 e to the minus 0.2x. And so this is one way we could go about solving it. After this next step, you might notice this is e to the minus 0.2x. This is the guy that looks weird. Got to get this guy by himself. And so if we want to get this guy by himself, he's being multiplied by 500. And so if we want to undo a multiply by 500, we have to divide each side by 500. And 5 divided by 500, there's a few ways I can write that. But that's 0.01. This is just 1 now. So we have 1 e to the minus 0.2x. And if maybe you're getting something from like these exponential functions, this is really kind of telling too. If we're going from 500 to 5 lumens, this was like my C, this is like my A. So my C is like my base amount, the A is like the factor. And so if you notice, this is like saying, hey, when is my factor the 1%? And so you could actually just start this equation here if you think like hard enough about this and what this means right here. But I like personally, I would probably start it here. Like I would suggest y'all start it here. But I'm just saying, like technically, if you look at this, you might be able to pick apart, hey, this is my factor, and this is like saying, when is it 1%? Okay. And if I want to do this, now I have my exponential all by itself. If I want something that undoes a natural exponential, the thing that undoes a natural exponential is a natural log. And so if I take a natural log of both sides, I guess I'll write this middle step in here. This side, we have this L and this E. These are inverse functions. The entire reason why I took log of this side was to get rid of those things. And so the left side looks like ln of 0.01. The right side looks like just this thing up in here, this negative 0.02x. And now I got to do a little bit. Ooh, this has an extra 0 in there. It should be negative 0.2x. Sorry. And now I got to do a little bit of solving. So x is going to be whatever the heck ln of 0.01 divided by negative 0.2. So ln of 0.01 So I believe this should give me something around like 23. And what are we talking about? Determine the depth. So 23.02, I guess, is what I'd probably round it to, or 23.03. In feet is what we're talking about. Well, maintenance is putting up a ladder outside. I think that's why the dogs are getting excited. Each little rung, they're bringing it up. It's like, let's get a little more excited. Okay. So this, I think, was sort of like I was talking about. They can give us an X to plug in here, or they can give us a Y. If they give us a Y, we're back solving on an exponential where we get this exponential by itself. We undo the exponential with the log. After we undo the exponential with the log, we solve this thing like we would just about anything else for X. There's this negative 0.2 being multiplied by the X, divide by the negative 0.2. My X is going to be that log over the divided by this number. And so that should give you around 23.03. They're talking about feet there. And so just to recap, at like 23.03 feet, that's where we're going to have 5 lumens, or like 1% of our light.
What was that I naught that you meant, that I with the little 0 down there? What is that? What is that?
I naught. So that means initial. Like the first one that was taken. It's where it starts. Anytime they give you like a naught, it means your intensity at time 0.
Okay, thanks.
Yeah. And this is really common, like sort of notation with the subscript 0. That basically means initial. That's where you're starting out. Oh man, what is this? This is a real thing, isn't it? In 1945, computers could perform about 1,000 computations with 1 kilowatt of electricity. This number has doubled every 1.6 years. I think this is called, what is that? Moore's Law? Is that what it's called?
Yeah, I think you're. Yeah.
Moore's Law. Let me look. Let me double check. I have the technology. Yes, Moore's Law refers to Moore's perception that the number of transistors on a microchip doubles every 2 years. The cost of computers is halved. So like this guy Moore made this sort of statement. It's not an exact sort of thing, but it's like they do this approximately, you know. They double every so many years, every 2 years, I think is what he said. And so in 1945, computers could perform 1,000 computations with 1 kilowatt hour of electricity. So I don't know if we've talked about this crazy thing, but they talk about kilowatt hours. This hyphen actually means multiplication. So this actually means like they're multiplying kilowatts times hours. And that gives you a unit for electricity. So this number doubled every 1.6 years. Okay. So find an exponential function e of x that gives the number of computations a computer can perform. I think this is supposed to say perform. It's probably a little easier for computers to perform than to perform. On 1 kilowatt hour, where x is years after 1945. So in 1945, they could perform 1,000 computations with 1 kilowatt hour of electricity. So we want to set this up. We want 1945 to be our base year. And so if that's our base year, the starting amount that they give us, or our C value, should be this 1,000 computations right here. And so I still need my A to the X. And we're just gonna jump right. I think I just jump into that, don't I? So they're gonna double every 1.6 years. So for doubling, the amount that we're multiplying by is
2.
Yeah, 2. And I'm not sure if we talked about this, but there's sort of like, it's a bit of a trick, I guess. If we want to double every 1.6 years, and maybe it's a bit tricky, but we want 1.6 to give us 1, right? As a exponent. Ooh, that is like really behind. Like 3.2 would give us what, 2? 4.8 would give us 3. And so how do we do this? This is division by the number 1.6. So if it's doubling every 1.6 years, what you do is you divide your exponent by 1.6. And hopefully that makes sense, because when after 1.6 years after what's the word I want to say? Not expires. After this transpires, I guess is what I want to say.
Elapses.
What was that?
Elapses works.
Elapses, yeah, that's the word I'm looking for.
Yeah.
Yeah, after 1.6 years elapses, we want to multiply it by 2 one time, right? If 3.2 years elapses, we want to multiply it by 2 squared, right? That thing is going to become a 2 squared. And then if we have 4.8 years it transpires, we want to do what, 2 to the third, which is what that's going to give us. And so I think this is the first time I've introduced doing this sort of thing. But if it doubles every 1.6 years, it should look something like that. And so this is our formula. We have everything in our formula that we need. Is this where they ask for an exponential formula? You're going to get where x is years after 1945. Okay. So they just ask us to find the formula there. And the next one they ask, in what year did computers first perform 1 billion computations per kilowatt hour? Okay. And so this 1 billion, I'll give you a hint, it's not this x value. It's got to be this e value that we're talking about over here. And so if we plug in a billion, 1,000 million, billion, and this is 1,000. So we plug in a billion, and now we're trying to solve for this x. And this x is in the exponent of a base 2. And so this is both of these things are in the exponent. So this is 1,000 times this crazy exponent thing. And so this is a crazy exponent thing. This is a multiplication operation. And so if we want to get rid of this thing and get the exponent by itself, we have to divide by 1,000. Dividing by 1,000 is like the same thing as saying take away 3 zeros from that thing, right? And so now we're going to say what? 1 million. So what is 1 million equal to the x divided by 1.6? Okay. Now we have this exponential by itself. If we have the exponential by itself, the thing that undoes an exponent, the thing that we learned right after exponents was logs. And so I want to take a log of this side, but the base of the log I want to take is a log base of
2.
Yeah, you can do it with different bases. This is just kind of my approach to doing things. So I guess buyer beware on that. There are other ways to do it. You could take a log of any base and then bring this down as an exponent in front. Some people like to do that. This is the way I go about things. If you want to see the other way, I guess there's always office hours. So I took a log base 2 of that side. I should also most definitely take a log base 2 of that side. I'm doing the same thing to both sides, so I'm not changing anything. Oh, wait, my table's getting smaller. Okay, so log base 2 of 1,000,000, and then we have this as log base 2 of 2 to the something. We took this log base 2 so that these two things would simplify out. And so now this looks like x divided by 1.6. This looks like log base 2 of 1,000,000. And you might have figured it out, but the last thing we do is if this is x being divided by 1.6, the opposite of dividing is multiplying. So if we multiply both sides by 1.6, we're going to get 1.6 log base 2 of 1,000,000. And now at this point, probably grabbing your calculator, we want to do 1.6 times log base 2 of 1,000,000. I'm going to cheat a little bit. What is this? 31.89, I think is what I'm getting. Okay, so this is giving me something around 31.89. This says, in what year did computers first perform in 1 billion computations per kilowatt hour? So we figured it's 31.89. You should probably round this to 32 to be safe. And so if we're rounding this to 32, and we started in year 1945, we have to do 1945 plus the 32. What is this, 1977? Questions about this? Sticking a little bit, hopefully. Example 4. So this is, yeah, there's a few different ways to do this. 9 to the 2x equals 9 to the 4 minus x. There's a little bit of a trick on stuff like this you can do. You might notice those are the same base, and if those are the same base, guess what we can say about the exponents? If these are equal and these are equal, I guess we could take a log base 9 on both sides if y'all really wanted to. But I'm hoping if you see it's the same base, those exponents absolutely have to be equal for those two numbers to be equal. If I really wanted to, I could take a log base 9 on both sides, and that would be like my next sort of thing, right? Log 9 of this. So if 2x equals 4 minus x, this is just a first order linear equation. You add the x. We get what? 3x is equal to 4. X is what? 4/3. Oh, man. I swear, like, this is like one of the steps people mess up the most on when they're doing those first order linear equations. Like, you got to divide those numbers in the right direction. Okay. So that one's a bit of a gimmick, I feel like. But these are a little bit more, give you a little bit more run for your money, I think. So 6 times this crazy exponential thing minus 4 equals 20. And so if you wanted to put your finger or your cap or whatever the heck, you can look at this thing and you can look at this thing, this entire thing, as 6 times something minus 4 equals 20, right? And this looks just like a first order linear equation if I just kind of ignore the fact that that's an exponential for a second. And if I'm solving this thing, the first thing I'm doing is adding that 4 to the other side. And so add 4 to the other side. So we get 6, 1.3 to the x is equal to 24. Same thing here. Now if I'm looking at this whole thing, this exponential as a variable, 6 times my pin is going to be equal to 24. The next thing I want to do is divide by that 6. And so I'm getting 1.3 to the x is equal to 24 divided by 6 will give me 4. And now I have that exponent all by itself. If I want to undo an exponent, the opposite of exponential is logarithmic. So I'm taking a log. Oh man, people. I've had other people make fun of me for doing weird base logs, but it works. And we're doing log of 1.3 to the 4th. I guess let it be known that every mathematician has their way and it's not all the same way. And so we're doing log of 4 over log of 1.3. That's giving me something like 5.2838. .284, I guess I go to 5.284.
This way seems like the smartest and easiest. What's the other way, and why do people make fun of you for doing what's simple?
This is just like whatever they get used to doing in their algebra class. I'll do it the other way, I guess. It's not too hard, and I got time. 6 to 1.3 to the x minus 4 equals 20. And so basically they would do everything the same way. 6 times 1.3 to the x equals 24. You get your exponential by itself. So basically at this step, instead of doing a weird base log, they would just take a normal either log or ln. And so we take a log of 1.3 to the x. You get the same thing, to be honest. you're essentially like forcing yourself to do change of base. And so they would take this step, and now at this step they would use your log properties. So we know this is an exponent. This can come down in front. And so x times the log of 1.3 will equal to the log of 4. And now this is multiplication. The opposite of multiplying is to divide. You're essentially going to get the same thing from the previous problem, just written out as like the kind of the change of base sort of thing, right?
Okay, thanks.
Sure. It is good to have different approaches, for sure. And you can do it either way. Personally, if you show your work and it's credible work and you're getting your solution in the correct way, you're doing the correct math for me. You know, I'm not.
And then you want us to go.
Yeah, I'm not trying to penalize anybody for doing correct math, but it does have to be correct.
And then and you want us to go to the 1,000 on the decimal?
Yeah, usually like 3 decimals pretty good, usually.
Cool.
It depends what you're doing, but it gives me a good idea you know what you're doing if you do 3. Usually. All right, last one, 1/2 1 minus x equals 1/7. You might notice that guy's already there. Okay. And so this is an exponent. This is an exponential already. It's got kind of a weird base of 1/2, but I can do the same thing I've been doing on the previous ones, and this is why I kind of like my approach as opposed to theirs. It just seems like it's a little quicker to get you there, but maybe I'm just seeing myself and have my own biases. So if I'm taking this, if I do log base 1/2 of 1/2 to the 1 minus x, and then I do log base 1/2 of 1/7. This side I did the same thing. So these two things sort of cancel out. And I'm going to be left with 1 minus x on this side. This is equal to this crazy thing, log base 1/2 of 1/7. If I want to solve for x, there's a few ways, but I can subtract 1. I guess I'll write it leading 1 log of 1/2 and 1/7. So I know I'm probably writing it a little weird, but I subtracted 1 from both sides, so I have a minus 1. The operation between these two things is going to be addition and subtraction. And now the last thing is, if this is a negative, I need to multiply everything by a factor of a negative. So this gets multiplied by a negative, it's going to be x. This gets multiplied by a negative, it's going to be positive 1. This I multiply by a negative will be minus log of 1/2 1/7. And so I feel like they're kind of giving you this so like you can do some more calculations. Can I take log 1/7, divide it by log of 1/2? Log of 7, can I divide that by like what, log of 1/2? 0.5, I guess, would be the easiest way to put it in your calculator. And then can I take 1 and subtract something like that? And so there's, I think they're trying to get you kind of primed to do like multiple steps in your calculator with something like this. So x is equal to negative 1.807. If this is actually, I like this solution almost better than this one, to be honest. This is an exact solution right here. This is an approximation.
Would either be good on a test, or would?
I would prefer to see like this right here, because this is what gets you to here. This is what your work's going to lead you to, right? And if you just like give me this number, it's not really showing me that you're doing your work. But the other thing, Yeah, the other thing I was gonna say is like you might need this. You might need the number itself if we're doing like a word problem, right? Like if we're doing math problems, this is good, but like if we're doing word problems, you're gonna need a number, right? Woo! I didn't delete something I should have. Example 5. So there are a few ways you can solve this one that are a little bit different. I wonder how I did it. Yeah, I did. So what I think what I did in my notes, and if you want, you can do this. This is 9. So if you want to think about this, maybe there's a weird way you could probably think about this that might save you some time. And so if we think about 9, if I want to rewrite that as like a smaller base, I can think about 9 as what? Like its prime factorization is going to be 3 squared. And if I think about the prime factorization of 27, it's 9 times 3. You can do a little tree real quick if you want, but it's 3 times 9 times 3 times 3, right? This is going to be 3 to the third. And so if I just replace these, you might notice that this problem becomes a lot simpler, a lot quicker. So instead of 9, I want to write 3 squared, which still means I have an exponent of x plus 5. And this is equal to, instead of 27, I'm writing 3 cubed. And I still have an exponent of 3x. And so you might notice that this is a base 3. And if we have exponents, 2 exponents, do you remember the exponent rule? If we have exponents, 2 exponents, the operation between the exponents, between 2 and x plus 5, the operation there should be did we do something like that? Yeah, we did something like that. So if I have 4 groups of 3s, I have 3 by 4s, or I have 12, right? And so the operation between exponents and exponents is going to be multiplication. And so we're doing this. This looks like 2 times x plus 5, and this looks like 3, and this looks like 3 times 3x. And so you might notice this is a base 3, this is a base 3. And so for those two things to be equal, then really these two things have to be equal. So I am basically solving a first order linear equation now. So let me pick it up a little bit. 2x plus 10 is equal to what? 9x. I subtract the 2 over, 10 is equal to 7x. X is going to be 10 divided by 7. So this one's a bit of a trick. I wouldn't use this approach to like go try to solve everything, right? It works on this one because it's a special sort of problem. They both have the same sort of base, right? They're both base 3. Their prime factorizations consist of only like 3s. So you can do this in certain situations. Okay. If a hot object is put in a room with temperature T naught, then according to Newton's law of cooling, the temperature T of the object after time T is modeled by this function, T of T equals. So notice like the case on this matters, right? The lowercase represents the time, the uppercase represents the temperature. Where D is the initial temperature difference between the object in the room, a pot of coffee with the temperature of 90 degrees Celsius is set down in a room at 25 and cools to 60 after 1 hour. And so they want us to find this function that models the data. Okay, so this, I admit, like it is a lot of information to take in upon first reading this thing, right? So T of T, they say T naught is the temperature of the room. So it is set down in a room that is 25 degrees Celsius. I believe T naught should be the 25 plus D is the difference between the object in the room. So 90 divided 90 minus 25 should be 65. Let me double check and make sure this is positive. They're not doing something negative. Yes, they're doing. Yeah, should be positive. So should be 65. Models. So A, we do not know, but it tells us it cools to 60 degrees after 1 hour. And so we do know our lowercase t. They give us 1 hour. So after 1 hour, and they did give us this thing. I didn't plug it in, but they did give us this thing. And so instead of T of T, I should really write here, after 1 hour, this thing is going to cool to 60. And so this thing is cooling to 60 after 1 hour. I guess I could have wrote an intermediary step. So I can fill in some of this stuff. This is 25, my D is 65, and I know A to the T. And so they give me a value when T is 1, when lowercase t is 1, the uppercase T is 60. And so I guess I could have wrote this out first and then plug this in is what I'm doing. And so now I'm trying to solve this thing. And I'm trying to solve this thing for A so that I can get a sort of general formula. And so we want a general formula. And so to look at this thing, I'm hoping you notice that if we want a general formula, we want only our lowercase t and our uppercase t. And so we really need to figure out what our A is. And so if we plug in a point, they gave us a point, we can figure out what our A is. So subtract 25, 60 minus, we'll give you what? 35 is equal to 65A. So divide that by 65. I'm getting A is like 0.53. Let me see how I put it in my notes. So save myself a little bit of headache. I believe I kept it just as a fraction. So A is equal to 35 over 65. If we divide both of those by 5, I believe we get 7 over 13. Okay, I heard a ding. Okay, so anyway, we have our A. We have this formula that was almost solved or almost plugged in. So T of T equals 25 plus 65, and my A is the 7/13, and now I'm putting in my lowercase t. And so now I have my general formula, and if they give me anything else about this scenario, I can find out what the temperature of the coffee is after however many hours, right? So the temperature of the coffee, the number of hours. And we're talking about this specific coffee pot now. find the temperature of the coffee after half an hour. And so if they say half an hour, this is like our lowercase t is our time. And so they're saying our time is a half. And so we're plugging in time of a half. So time of a half equals, now our formula looks like 25 plus 65, 7/13 to the half power. And so maybe going over like some PEMDAS, we have to do exponents first, we have to do the multiplication, and then we have to do the addition. Okay, so you should be able to do this in your calculator. And I'm hoping you get something like 72.7. So this is a good time to do a calculator check and make sure you can operate your calculator and make sure you're getting these numbers. Now is the ideal time to do that. And now we're talking about 72.7 Celsius. And so that one, they gave us a temperature, or not, they gave us a time, and then asked us to find temperature. The other way around is they can ask us well, let's pretend like that's not there. They can ask us a temperature, and then ask us to find what time was it at that temperature. So if they're giving us temperature, now they're giving us the capital T value. So now the capital T is equal to 50. Our function still looks the same, 25 plus 65, 7/13, and now we want to solve for this T variable. I don't know why around this time it always says my internet connection is unstable, but Zoom's always giving me that message. Okay. Let's hope it never does anything. But if we want to solve this, this is what we've been doing today. We want to solve this exponential. This looks like 25 plus 65 times my pin is equal to 50. Well, if I was solving this, and this was just like a linear equation, the first thing I do is subtract this 25. So 25 is equal to 65 times whatever this crazy thing is, 7/13 to the T. Okay. Same thing, if this is my variable over here, now I have 65 times my pin is equal to 25. Well, this is multiplication. The opposite of that is going to be division. So I want to do what? 25 divided by 65 should be giving me a crazy number. That's not pretty. 5/13. So 25 divided by 65. I'm simplifying it. But I divide 25 by 65 and I simplify it, it should give me 5/13. So I divided the two, then I converted them to a fraction, right? Okay, so we have 7/13 to the T equals 5/13. Now, the name of the game was to get this thing by itself. Oh man, I see something that looks so tempting, and I want to say it. Can I multiply by 13? That would work over here, but if I try to multiply by 13 over here, I'm hoping you can see this thing has an exponent. If I multiply by 13, this thing is not going to have an exponent. So if I try to multiply through over here, that's not going to work. Don't try to do that. Do not do that. Do not multiply by 13. So I'm giving you a really bad idea, and I'm trying to tell you not to do it, right? Trying to save you some heartache there. But anyway, we want to get rid of this thing. So my approach is just to go ahead and take log base of this crazy thing. And so I do it that side, got to do it this side. Y'all can see that, okay. So I did it to that right side. I did it to that right side because this is the log of the base. These two things should simplify out. And so that should give me my variable t. So t is whatever the heck that left side is, which was log of 7/13, log base 7/13 of 5/13. Okay, so now everyone do this by hand. No, you're definitely doing this by calculator. So this is about 1.54 hours is what I'm getting. I feel like that would like be the meanest thing, just like try to get people to do that by hand. Yeah. Don't even ask me how, I have no idea. So this is log of 5/13 base 7/13. It's a crazy thing to put in your calculator, but you can do it. It'll give you like 1.54. So let's think about what we're talking about here. The original question was, when is my coffee going to reach 50 degrees Celsius? And so this is the other thing, the time, and the time was measured in, I believe, what was it, hours? Hours is what we were measuring it in. So this should be hours, after 1.5 hours, basically. But I'm also hoping, like, maybe this makes a little bit of sense. If you think about, like, how coffee warms or cools, remember this was the sort of exponential shape that we had. It kind of goes like this, and it increases, and it slowly increases. So it works approximately exponential, right? Or not exponential, logarithmic. If you want to compare time to the temperature.
Just for fun, you know how you did the 1.6 equals 1 earlier? You could change that 1.54 into minutes with more math? Like by
Yeah,
I
so
mean,
if
see
you
what
want to
I'm
go to
saying?
minutes, is that what you're saying?
Yeah.
So multiply this by 60, right? We'll give you minutes.
It would just be that easy.
Yeah. I don't know. Oh, there's a cute little thing I learned in like, how was like fourth? No, maybe it's fifth grade. It was my teacher, Miss Thomas. I remember her for the rest of my life. But she used to tell us, like, there's a little saying, it's big to small, multiply all. And so we're going from hours to minutes, you're multiplying. Big to small, multiply all. Small to big, divide the pig. I will remember that for the rest of my life.
Nice.
Oh, man.
Could you maybe show us how to do that last part with the calculator? For some reason, in my calculator, I'm not getting the same output.
Okay. I'm hoping I did it correctly. Okay, so 5 divided by 13. That's the top one. The bottom one is log of 7 divided by 13.
Okay.
Trying to
Got
think.
it.
Yeah, there shouldn't be any kind of weird mode or anything.
So you divide them.
Yeah, it's the big log over the little log.
Okay, right.
The
Okay.
change of base formula. Yeah.
Right. Okay. What about the one before that on B? Could you show me real quick how to do that on the calculator? Awesome.
Okay, so if you're going to take 7 divided by 13, and we want to raise that, to what, 0.5?
Yeah.
So that gives me that crazy number.
Okay.
I want to multiply that by 65.
Yeah.
And then I want to add 25.
Okay. Yeah, I don't know. I'll have to mess with it. For some reason, my calculator's giving me something different. Okay. Cool. Thank you.
Okay. Sometimes you might want to check the modes. I don't know if there's maybe some weird mode that's setting it off. I don't imagine any sort of mode would really mess with that too bad, though. I think that's more common when you get to your trig and you're doing your radians versus your degrees. It's really where that comes in a lot. um, mhm. Okay. That is example 6. Example 7. Okay, so a fossil contains 60% of the amount A of radioactive carbon-14 that the organism contained when it was alive. If the half-life of carbon, okay, so this is talking about carbon-14. So carbon-14 is something, it's a radioactive substance that is within every living organism. Is that, like, where's that noise coming from? Is it my echo?
Sorry, that was me.
Okay. I don't even see the mic. My mic is the only one, like, even kicking over there. Okay. So this is about carbon-14. So carbon-14 is a substance. It is a radioactive substance. Not like there are different forms of radioactivity. This is obviously not like one of the dangerous forms of radioactivity. But every living substance produces this while they're living, and then when they die, they quit producing it. And so this is something that we take a measurement of, and we can determine like the date of the death of the organism, right? And so we use carbon to date the organism. You might notice, oh, wait for it. You might know this by the name of carbon dating, right? This is how they do carbon dating. Fossil contains 60% of the amount A of radioactive carbon-14. The organism contained when it was alive. The half-life of carbon-14 is 5,700 years. Use this formula. You might notice this is a base of a half. So we're having this every 5,700 years. So we're using this formula to determine its HT, where C is the initial amount or percentage of carbon-14. Okay. So there's a few ways we can think about this. If we start off, I guess we could just throw in percentages if you really wanted to. You can come up with numbers if you want to. But if we said we're starting out with 100%, I guess I should just shut up and do it one way or another, huh? A half, this is T divided by K. That K is a constant. We want it to half every 5,700 years. So this is sort of like coming from that previous problem. If we want to multiply it by half for every 5,700 years that we go through, we have to divide this number of years by the number 5,700. And so that's where that K is coming from. It is coming from your half-life. So K is your half-life. C is the amount that you start off with, and this is the amount that you end up with. T is the amount of time in years, or whatever the heck they're giving their half-life in, which is years here. They could technically give the half-life in a different unit, I guess. And so we're going from 100, or if we start with 100 milligrams of this thing, and we want 60%, 60% of 100 is going to give you 60. So if you pick easy numbers to do, like 160, you might be able to do this. That's one way to do it, but you might notice we're looking at this here. The first thing we're going to do is divide by 100. So the first thing we're doing is converting this to a percent. And so this is sort of like I was saying before. You can look and throw amounts in there for the initial and the final amount, or you can just look at this factor and say, hey, when is this factor going to be 60%? So this is like an initial amount. This whole thing is like some crazy factor we're multiplying by, and then this is like the final amount. Or you can just think about the factor by itself. And if we think about the factor by itself, now we have a base of a half. We have this exponent by itself. And so if we want to get this thing out of exponents, log base what? A half? of 0.6, I believe is what we're doing on that side. If we log half of this side, so I don't want to write like this over and over again. So I'm going to skip a few steps, but log base of half of this side is going to simplify out this thing. That's the reason why I'm taking it. So this side should be T over 5,700. And now I'm just solving for my T. My T is being divided by 5,700. So in order to get that on the other side, I want to multiply by 5,700. And I'm doing 5,700 times log of a half of 0.6. And now it's calculator check time. Can we do log of 0.6 over log of 0.5? You could probably convert that to 0.5. It would save you a little bit of time. We divide those two logs. We multiply by 5,700. I'm getting something around 4,200.7, which you might as well just round it to what? 4,201 years. Am I coming up on there? Okay. Yeah, I would say like I feel like these are more the problems that you'll see are stuff like this where we plug in, we have to back solve some exponentials. More so than that one that I said was like a special strategy or whatever. I would concentrate more on these sorts of things. This one, you might have something like this on your homework. But this again, like I would say this is a bit of like kind of a special strategy. But I'm hoping you can see in here. This is an e to the x. This is an e to the 2x. Maybe it's kind of silly, but e to the 2x I can write as e to the x being squared. And so it's like we have an e to the x being squared. We have one of them, and we have a constant term with none of them. If I want to write e to the x as y, I guess I could write it as a y, but this would look like y squared minus 4y plus 3 equals 0. And I know you thought you were completely away from these things, but not quite. They're still coming up. This is a quadratic. Are we still there? Okay. Okay, so this is a quadratic. We've done a lot of quadratics all throughout this course. I'm hoping you know how to factor things at this point. But if I factor this thing, and let me just write my substitution up here. I substituted y for everywhere I saw an e to the x. And so if I make that substitution, I think it might be easier to solve it with the substitution. This looks like y squared minus 4y plus 3. This looks like what? Y minus 3, y minus 1, I believe, is what this factors into. When we do minus 3 minus 1 gives us the minus 4. Minus 3 times minus 1 gives us positive 3. And so you might notice you're getting something like y minus 3 equals 0, y minus 1 equals 0. This one is giving you the y equals 3. This one is giving you the y equals 1. And so that's good if we want to solve for y, but they asked us to solve for x. And so this is kind of like that u substitution thing I've done before. But I plugged in y for everywhere there's an e to the x. Now I need to plug in an e to the x everywhere I see a y. And so instead of y, I'm writing e to the x is equal to 3. I'm writing e to the x is equal to 1. If I want to solve this, I take a natural log of both sides. If I take a natural log of this side, it undoes the e. If I take a natural log of this side, it looks like x equals ln of 3. Same thing here. Take a natural log. This is going to look like natural log of 1. And I really, anything to the what power is 1? This is that 0. So anything to the 0 power is going to be 1. That means ln of 1 is always going to be 0. Or log of 1, any base is going to be 0. Quick recap. Did we talk about, well, we did talk about this. Do you remember ln is 0? E to the what is going to equal 0, right? Or something like that. We talked about this. What is this? What is ln of 0? ln of 1 is 0. ln of 0 is
Undefined.
Yeah, this guy's undefined, right? So don't forget that. Like, maybe keep that in the back of your mind somewhere too. Huh? Okay. Okay.
So are the answers then log of 3 and 0?
Yeah. So if you want to do, hey, chill. You're being bad. I'm trying to teach over here. Yeah. Okay. Sorry about that. So this is x equals ln of 3. They are like rambunctious this morning. I don't know what their deal is. So I guess if you wanted to give me an approximation, you could give me something with that, you know. But ln of 1 is 0. But I prefer the exact solution, to be honest. I prefer the ln of 3. This one, you could probably give me the 0 since it is 0. But if you gave me ln of 1, if I'm being honest, I probably would give you 100%. Go sit. And so we just have a few logarithmic equations to solve. Okay. So let's do these. So this is the same approach. There were some rules, but they basically say the same thing. Get the weird guy by itself. So this is my weird guy right here, my log of something crazy. So I have 4 times something equals, 4 times this junk is equal to 6. So if I had 4x equals 6, first thing I would do there is divide by that 4. So I'm doing 6/4 or 3/2. Maybe I should simplify that. And so log 5 of 2x is equal to 3/2. And so there's a few ways I can do this. I can exponentiate everything with the base 5, or I can look at my log properties and do this sort of thing. 5 to the 3/2 is going to be equal to that thing that's on the inside of the log. And so that's coming from the definition of my log. Either way, you're going to get the same thing, whether you do the inverse property or whether you do the definition of the log. You should be able to get to this step. Once you get to this step, probably definitely using a calculator to find out what 5 to the 3/2, that is not a pretty number. But in order to solve for x, we're going to have to take 5 to the 3/2, and then the other thing to solve for x is we're going to have to divide that by 2. And so if we take 5 to the 3/2, divide this by 2, it should be giving us something like, ooh, I don't have that on there, 5.5901 or 5.59 is probably good enough. Okay. So we want to solve this thing. So if we look at this equation, first thing we want to do is get the log by itself. So on this equation, you might notice our log is already there. So if we want to take this, we want to do the definition of the log. So what this is telling me is 2 to the third should be equal to 4x minus 2. So if I just go follow my definition of my log, I will get something like this. I get something like this. This is a first order linear equation. You should be able to solve these things by now. So we add the 2 over 4x is 10. We divide by 4, it's what, 10 fourths, or x is 5 halves. Any questions? So we got 2 problems for our written homework. I think I'll probably hit the record button pretty soon.